One of the most interesting elastic collision is billiard board. It's a two-dimensional collision, and it's a collision of where all the balls, they have the same mass, and we were trying to use the cue ball, which is the white ball, trying to use the white ball and make other balls fall into the pocket. Okay. If you haven't played it, you can find such a game in some bars or maybe in your friends' houses. And anyhow, today I'm going to talk about the physics behind that, and you can use this technique in the real game to win your friends. Okay. So first, let me talk about theory behind that. Again, we talk about that because the thing is that you want to use one ball to hit another ball. So this is a very typical collision problem. And this collision type is that the first ball and the second ball, because all the balls on the billiard in the pool, they all have the same mass and the same size. So now let's study this specific situation where all the masses are the same and the second ball is not moving. Okay. So imagine that when you're playing the pool, this is your cue ball and this is your target ball. And you can use your pole to hit the cue ball, so that your cue ball will start rolling with the velocity, we call it v1, where your target ball is just not moving. And then after collision, your cue ball may roll in this direction, and your target ball may roll in another direction. Okay. So how do you predict, which direction it is going to and what's their final velocity? So to make that prediction, let's think about this. So basically, this type of collision, the billiard boards, it's created in a very in a very perfect way. The shape is perfectly spherical, and it's very hard. So there's no like sticky, or no rough part at the surface. So this is a nearly perfect elastic scattering or elastic collision. And since it's a perfectly elastic collision, the momentum will be conserved, and so does the energy. The momentum conservation here in this case, because it's two-dimensional, so the momentum, we know it's a vector, so momentum will be conserved in both the x direction and the y direction. When you watch this video, we probably haven't covered 2D collisions in the lecture yet. So here I'm just gonna give you a brief overview. So first, let's look at the momentum in x direction. The momentum in x direction, you can see initially, it's only the cue ball rolling. So the momentum is completely in x direction. So the total momentum before collision is just m1 v1. Okay. And however, the final momentum collision and the final momentum after collision, it has the momentum of the first ball and the momentum of the second ball, they both have some part of x component, right? So the first ball has the momentum of m v1 prime. The second momentum has the m v2 prime. But its x component is not that much. For example, this guy, the v1 prime, this guy has a momentum mv1, but its x component is only this much. Okay, only this much. That's adjacent of the angle, so it's cosine theta 1. And similarly, the second ball, this one, it has a momentum, but not completely x direction. So we need to find out its x component. Again, it's also a cosine. It's adjacent of the angle, so it's cosine theta 2. So similarly, we can look into the y direction. Before collision, you can see there's no one moving in y direction, so the momentum in y direction is 0. But afterwards, you can see the first ball has part of the momentum in y direction, and so does the second ball. And this ball, that would cancel out because their initial momentum in y direction is 0. So that's what we know from momentum conservation. And now, since it's elastic, so the kinetic energy is also conserved. And since kinetic energy is conserved, we can see initially we have a kinetic energy mv1 1/2 mv1 squared. Final, after collision, we have two kinetic energy, which is 1/2 mv1 prime squared plus 1/2 mv2 prime squared. So totally, you can see we have 1, 2, 3, 4. We have 4 unknowns, but we have only 3 equations. So no matter how hard we try, we cannot really solve this problem. We cannot really solve for v1 prime equals to what, or v2 prime equals to what. But since we have some constraints, so we can still constrain our answer down to the following few situations. So this is the first situation. In the lecture, I'll show you how to do the math. But here I'm just gonna show you the result and how we apply this result in billiard boards. So the first result, the first possible scenario of the first answer solution to this set of equations is v1 prime is 0, v2 prime is v1. What does this mean? This means when my cue ball hit my target ball for the velocity of v1, then this will be a head-on collision, where once this cue ball will stop right before the cue ball will stop right before the target ball, and the target ball will move forward with the velocity of v1. So this is talking on a head-on collision, like when you hit the ball, this one coming and transfer all of the momentum to the second ball, and the second ball goes off. This is a head-on collision. The second scenario is the ball comes in, but the target ball is here. So you can see that cue ball completely missed the target ball, so the cue ball just keeps going forward with the v1, while the target ball is still stay at the same place. So in this scenario, v1 prime equals to v1, v2 prime is still 0. This is a scenario that you miss the target at all. Like you don't even touch the target ball. Okay. So these two scenario, one is a head-on like a collision, one is you miss the target. Most of the time, your ball will be more like in the third scenario, where you're not completely heads-on, but you're not completely miss the target. You're just, it's more like this is your target ball, and your ball goes somewhere like this. It hits like the corner or like some part of like off center of the target ball. When this happens, your target ball and your cue ball, they're going to go in 2 different directions. Okay. And these 2 different directions, it will be perpendicular to each other. It means that theta 1 plus theta 2 equals 90 degrees. So after collision, so you imagine the collision is coming. Let me draw a picture here. So imagine this is coming to this, but slightly off center. Okay, not completely in the center, it's slightly off center. I'm gonna draw a better picture. Okay. Slightly off center. Okay. When this happens, the cue ball will roll in one direction and the target ball will roll in another direction. And the angle between their path is 90 degrees. Okay. This is the third scenario. All right. So now you know all the physics and the solutions to these elastic collisions. Now I'm gonna show you the, like we call like a beginner trick for pulling. This trick is called ghost ball. I'll put a video explained by other professional professionalist on skies. Here, I just want to briefly talk about the idea. So for example, when you use your ball to use your, when you aim your cue ball to your target ball, and your goal is to make this target ball goes this direction, goes into the pocket, like here. So this is what you want the target ball to do. So how would you aim your cue ball? Would you aim it with this trajectory? Would you aim it in this direction or that direction? So ghost ball is saying, since we want this ball goes into this pocket. So we want to make sure the collision point is here. We want to make sure this cue ball will hit the target at this point, so that collision, the momentum, because this momentum will be a normal force. So this momentum will send my ball in this direction. And to make my ball have a contact, to make the contact point at this position, you want to make sure you send your cue ball all the way here. Okay, it's a little bit hard to draw the picture. I'm gonna try my best, but this, okay, this is my contact point. Okay, so I want my ball, I want this ball to be here. Okay. Usually what people do is that they will put another ball on the table to help them image. Okay. So as long as you hit your cue ball into this direction, then your cue ball will be in contact with your target ball right at this contact point. And thus the momentum will be transferred into this target ball through this contact point in this direction. And after the collision, your target ball, so what you should do is you should aim like half of the ball behind the target ball. So when the cue ball comes in, your target will go in this direction, and then your cue ball will go in this direction. Let me use another color. Okay, your cue ball will go in this direction. So where this is perpendicular. Okay. So that's your cue ball. That's your target. So this technique is called ghost ball. And you will try this out on a simulation in the lab. All right. So this is a very simple, like a beginner trick, and definitely try it out by yourself. You will be amazed by like how accurate this rule is. But of course, you know, like all of our assumption is that it is a head-on collision, so you don't want to add any side spin or front spin or back spin to the ball. All of our analysis here, assuming the collisions are head-on collisions. Okay. So I hope this is an interesting application for you. And yeah, and I'll see you in the lab.